Hello, and welcome back. I hope you had a great lunch. So let's jump right into our next speaker. Aladdin Persson is a machine learning engineer. He's a YouTuber. He's making very good YouTube videos. I learned a lot of stuff from watching his videos. He's a dear friend. And today he's going to talk about language model in recommendation systems. So let's give him a big round of applause, and let's hear the talk.
Thank you so much for the introduction, Francisco, and very glad to be here today. So in the last few years, large language models have taken over machine learning. Today, we're going to dive deeper into how LLMs are taking over and being used in what I like to call the silent giant of our industry, which are recommender systems. My name is Aladdin Persson. I'm a machine learning engineer. 2 years ago, I founded my own company, Nanai, where I primarily provide machine learning consulting services. Currently, I'm working on food recommendations at Walmart. And as Francisco said, I also have a YouTube channel where I share what I'm learning about, things that, basically my journey through AI. Large language models, we hear them all the time. We hear them from friends, from family, in the news, on social media, getting bombarded on LinkedIn, X, Twitter. And we can also see it in terms of the statistics. So, ChatGPT, when it was launched in late 2022, only took 2 months before they reached 100 million users. And since then, we've seen continued steady growth. And personally as well, it's difficult to imagine if you now removed AI-assisted coding and all that we have in our workflow as engineers. And I know as well from a lot of friends who work, are knowledge workers, attorneys, etc., are using these tools, and they've become really integrated into our life in a very short amount of time, since it was just 2 years ago that it really took off. If we look at the actual performance of LLMs, they are also incredibly impressive. So this chart was from GPT-4, basically GPT 3.5 Turbo to GPT-4, and this was over about 2 years ago. And so if we look at sort of general US exams on, this is a wide variety of topics like calculus, chemistry, history, psychology, biology, etc., it actually performs better than most human test takers on these tasks. So they're really powerful world knowledge models. And in some cases, they also surpass the performance by quite a lot compared to humans. And interestingly, there's one that's I think the third blue one, that's in the bottom percentile of Code Force's rating. And if you would take the LLMs today, then we would perform above the 99th percentile on this task. And this was just 2 years ago. So Sam Altman, 2 weeks ago, also wrote on X, "Goodbye, GPT-4. You kicked off a revolution. We will proudly keep your weights on a special hard drive to give to some historians in the future," kind of symbolizing the extreme progress we've seen over the very short amount of time. Now, if we look at our LLMs actually internally, so we've had a lot of speakers today talk about LLMs, and you're probably familiar with this as well, but it's worth emphasizing again that language models are next token prediction models. So they're autoregressive, and meaning they basically take the context of, let's say there will be 2 words, dead dog, then it's asked to predict what is the word that comes after, right? So the next token in that case, the most probable one might be the dog sat, and that would be time step 2. Then we would go to time step 2, which would be input to the model, would be the dog sat, and then we would predict the next token, which it might be down. So that would be time step number 2, the dog sat down. Again, we ask it, predict the next token, and at that point it might say, all right, end of sentence token, we don't want to predict anything more. That's the end of the prediction. So again, it's a next token prediction model, and also importantly to note is that it has a fixed compute budget. So it only has a certain amount of parameters, and it's only able to do a certain amount of compute in a single time step. So this makes it really interesting because from that fact, we get interesting things like chain of thought reasoning, where you don't want to make any single token too advanced for the parameters of the model, and you basically want to split the reasoning so that it does it over many tokens throughout time. Thirdly, I think, and this was, I believe I got this from Andre Karpathy, and I believe it's a very good way to view LLMs, which is that LLMs, the parameters of the LLMs, they're essentially a distilled, a heavy loss compression of all the data that it was trained on. So imagine, we have all the world internet data, which might be hundreds of terabytes of text, and we basically compress that in a heavy, heavy way to maybe 30 gigabytes or 50 gigabytes, depending on the number of parameters of the model. And so things that it's seen very frequently in its data, we will have very good ability to recite. But things that it's seen very seldom is going to be harder, and it might start to hallucinate. For the actual training of LLMs, and how they're actually trained, they usually go through 3 steps: a pre-training step, a supervised fine-tuning step, and a step including reinforcement learning. And if we look at the sort of how expensive they are, the pre-training is definitely the most expensive part, and this involves essentially taking a lot of text data, and we just ask it to do that task of next token prediction. And this is, that we've done previously as well. GPT-1, GPT-2, GPT-3 were all next token prediction models. And they were many, many years ago. In fact, GPT-2, when it was released, they didn't release the weights for the model because it would have negative societal impact, so we don't want to share it. And if you compare, GPT-2 to what we have today, it's an enormous difference. But really, in 2022, there was a paper called Instruct GPT, which that paper showed that if we have 100 less parameters, but we train the model in a way that it's managing to do dialogue. So we give a message, and the assistant responds in a dialogue format, instead of just doing next token prediction. Even though it has 100 times less parameters, it is still preferred by humans. And that is one thing that made it take off and be much more aligned with how humans like to interact. The third step usually involves reinforcement learning. And the third step here of the reinforcement learning is really where we've seen a lot of progress in the last, in the last models. And I think notably here, DeepSeek is one of those that kind of showed us how to do the practical implementation of the reinforcement learning aspect. And what you can think of it is basically we're giving it free ability to reason and think about stuff, as long as it's able to come up with a final verified answer. So we might give it a lot of math problems to derive certain formulas, or come up with some code. And what we do in the end is basically check, all right, well, does the code compile? Does it check all the test cases that we have for the code? And if it does, we give the model a reward, and it's able to figure out the reasoning parts on its own. And I think this is really key for how we get these models to really perform magic, and when we kind of let them interact and play with itself through reinforcement learning. So this is a really interesting field. We are now starting to see LLMs used a lot in the recommender system space. And I like to view recommender systems as the silent giant of our industry. And let me explain a little bit, why I say that. So recommender systems, if we look at the actual revenue and engagement driven by recommenders at the big tech companies. So if we look at Amazon, Netflix, YouTube, Meta, and we basically, by public statements of these companies, Amazon has stated several years ago that 35% of all their purchases comes directly from recommendations. Netflix, 80% of their watch times comes from recommendations. YouTube, about 70% comes from the recommender system that gives video in the feed. For Meta, we don't know exactly, but they say that around 80% the actual compute cycles that are on their compute clusters are driven to serve recommendations. And so if we think about these companies as well, right, if we just imagine how they work, we can see that it's really fundamental, these recommender systems are really fundamental to how they work. And if we remove the feed of Netflix, then there is no Netflix. And so they are really the building block and the fundamental layer for how these companies are able to generate revenue and function. If we contrast that to, let's say, the paper count distribution of research in academia of what are people actually researching, right? So we have most papers coming in computer vision, in NLP, and for recommender systems, we see like a very, very small piece of that cake at 1.8%. And it's comparable to something like federated learning, which federated learning is like a very cool idea and a very cool concept. But if you look at if you would compare the two, right, of what is the practical industry impact of the two different areas, we would see a huge mismatch. And so this is why I call RecSys a silent giant in our field. So what about RecSys before LLMs, to get sort of an idea of how the field has evolved and how it looked like? And if we go really far back, I think they believe the first recommender system that was in some production was in the 90s, in 1994, of Group Lens, where they basically wanted to recommend news articles to users. And so they did a very simplistic solution where they basically looked at, all right, what has this user liked? Which news articles have they liked? And which are the users that are most similar to this user? And then they just look at, all right, which news articles do they like? And we can recommend that one to them. So using some kind of Pearson correlation or something like that. And shortly thereafter, we see Amazon doing something very similar, but doing on an item-to-item basis. And that was really that kicked off a lot of recommender system use in industry. Then if we go to the Netflix prize competition, it really drove a lot of innovation as well, coming up with matrix factorization. So this is, we used a lot of linear algebra with singular value decomposition to break down the matrix, and that's how we used to recommend. And shortly thereafter was new methods as well with SVD++ and so on. Then in 2015, we see really early work using deep learning in the field with GRU for Rec. 2016, I would say, was really the year that deep learning and recommender systems took off. So we got two really key papers, YouTube Deep Neural Networks and Wide and Deep by Google. So this is actually where the first show of using two-tower architectures that we heard from Florian earlier today as well, of having a candidate generator that is more lightweight model, and it takes, let's say, millions of YouTube videos and brings them down to a few hundred or so, and then we would have a ranker model that would be larger, usually more sophisticated, and be able to re-rank those candidates. So that was from the paper YouTube DNN. And then Wide and Deep basically was Google's, they were showing how they were doing ad click prediction. From there, we saw further improvements with how these architectures were implemented, with being able to learn features in a better way, with learning features deep and cross, also by Google. 2019, DLRM by Meta, which kind of optimized those kinds of architectures, very simplistically said, but basically. And then 2018, 2020, we saw a lot of graph neural networks, PinSage, like GCNN. We saw self-supervised learning with the whole SimClare and contrastive learning papers. We saw that being used in recommender systems as well. And now we come to LLMs in RecSys in 2023. So what are the key, why are people interested in this, right? I would say one thing is that LLMs have shown that they're able to be extremely powerful general purpose models. So you can give it a lot of different tasks and it performs really well on basically all of them. And it also scales really well with compute. So if we look at RecSys, they've basically had a very hard time with being able to use a single model. So if we look at production systems at Meta or LinkedIn, Netflix, et cetera, they usually have 30 plus specialized models, teams working on each of those. And in RecSys, we're constantly fine-tuning new models, and so a lot of engineering effort. And if somebody could say, hey, you can just use one model, that would be a lot easier, right? And the fact that it can also do a lot of cross-learning within tasks and scale a lot better as we give it more data. So what about LLMs in RecSys? What are the main areas, the categories, I would say, that we're seeing them used today? The first is quite natural, I would say, in more conversational and agentic workflow. So, they excel in conversational tasks, and if we saw some examples of that in talks today too, of how we can hook up tools to those and make them agentic, and so they're able to do the recommendations using those tools. Secondly, we see them a lot in RecSys being used for feature engineering / tagging. I'll go a little bit more into each of these. We also see them used in generative agents for evaluation. Offline and online evaluation of RecSys usually has a wide gap, and if we can bring that gap closer and evaluate models offline, that is a very interesting thing that we can do. And fourthly, I would say autoregressive RecSys. And there's some different paths people are taking in autoregressive RecSys, and we'll dive a little bit deeper into that as well. So conversational and agentic LLMs, kind of what we described briefly. We might have a UI where they interact with movies or TV shows, and we know that the user likes Big Bang Theory, for example. We can easily hook that up to an LLM agent where it has access to a vector database of all the previous movies and embeddings for those, right? And we can just do a cosine similarity, add that to the LLM, and it's able to recommend. And in that case, it might recommend how about the IT crowd as an example. And we could give it more tools as well. We could give it a vector search, but we could also give it web search and things like this. So we see this being used a lot for companies like Walmart, like Amazon. They're all very interested in how we can build a shopping assistant that can do this directly in chat interface. So this is from Walmart, where the user might ask, what kind of TV should I buy? I watch a lot of soccer. And they basically say, you want to have something with high refresh rate, you want to have this size or something, and then they give you a few recommendations. So this is how it could look like in practice. Then LLM for tagging and feature engineering. This is from LLM for tag. It's a very simplistic kind of architecture here. But basically, we have an image. We might have some tags that are suitable for that image, and we have a prompt that we give to the LLM, given these tags, which would you say are fitting for this image? This is a very simple diagram that they show how to do it. But there are more sophisticated ways we can imagine how we build this so that we actually get better performance for tagging. And this is key for recommender systems, because if we have items tagged, we can easily create filters from the user, and this is widely used. Then a very interesting area, right, that we mentioned, LLMs as evaluation engines. So I don't know if you recall the paper, generative agents, where they played within a game and they interacted with other LLMs, et cetera. That was a really interesting paper, and they've kind of done very similar in RecSys, where the idea is basically, we have a starting point where we look at, all right, these are the transactions or the interactions of our user. From that, we can do a persona matching. So we can say, like, okay, this user likes these kinds of movies. It might have this kind of personality. They like to watch a lot of movies. They like a wide variety of genres, etc. And so from that, we create, in the paper, generative agents for recommender systems. Basically, they did 1,000, I believe. So they did 1,000 different agents with different personalities that we add to the prompt. And then they basically did like a sensing prompt. So they did captioning on all the items that it saw. So it might see a row of movies, and it extracts first the caption of what it's seeing so that it's able to know what the feed looks like. Then we have a watching prompt. We basically ask it, based on your personality that you have and what you like to watch, which ones out of the feed would you click on and be interested in, and give a reason to why. And then we can ask them, all right, for the ones that you actually wanted to click on, what do you actually think of them? What would you rate these movies? And then it has basically, you can imagine how you interact with the first items might impact how you interact later, right? If you scroll and none of the 6 first items are interesting to you, you might become a little fatigued and you might want to close, exit Netflix or something. So then basically that gets embedded into the LLM memory module that it can see like, okay, I didn't click on any, now my fatigue level goes up, my interest is a little bit down, etc. And then it can choose to exit the recommender system, and it gives an interview, basically a feedback of what it thought, its general experience, and so on. And this is really interesting because this means that we can now evaluate in a really powerful way, because we know that LLMs are very powerful and can simulate people. We can run sort of behavior studies, etc., using these LLMs. And bring the offline and online gap a lot closer for how we evaluate them. Autoregressive RecSys, the 4th category that I mentioned, is essentially, so autoregressive, right? We talked about this. It's a next token prediction. And so there's some interesting ways that people are implementing this within recommender systems. Here's one paper from P5, which was a little bit early in 2022. Recommendation as language processing, a unified pre-trained personalized prompt and predict paradigm. And it basically did basically a lot of different tasks in one. So we would do sequential recommendation, where we would say, these are the items I interacted with, and I am this user. This is the flow of the interactions. And they just put them into text and then predict what is coming after. And then they could do that for a lot of different, like rating prediction, explanation generation, review summarization, and direct recommendation. Now, what I want to emphasize here is, all right, so it's obviously autoregressive, right? We're predicting the next token. But the key sort of divergence of what people are doing now is that they're saying, all right, well, we can do it directly in text domain. But the problem is that we really have items, right? We have movies that if we have, like user underscore 15466, that might get split into 6 different tokens with our tokenizer. And so it's very hard to learn in a good way. And what they propose, or what you can do, is you can expand your text tokenization vocabulary, and you can add, let's say, you have 100,000 for text, you might add 50,000 more, which are for specific movies and users. And so when it sees user underscore 15466, it gets its own embedding from the tokenization. And this is what I wanted to talk more about. So I split autoregressive RecSys into text tokens and item tokens. So this is from a paper this year from 360 Brew from LinkedIn, where they trained a LLM in text tokens only. So they didn't add any tokens, anything like this. You can imagine the previous one that we saw is kind of like a hybrid. It has text tokens and you might add item tokens, right? So then you have a hybrid approach. If you only go with the standard text token approach, this is for job applications. So the instruction might be, you're provided a member's profile and a set of jobs, their description, etc. And we say the member profile. So the current position of this member is software engineer at Google in Sunnyvale, California. They've previously applied to these jobs, at these locations, etc. And then we just ask a final question: will they apply to this job posting that we want to recommend them? And it's very simple, right? And they did this, and they trained it end-to-end, 150 billion parameters, and it surprisingly works very well. So they beat their production systems, like 75% of their current production systems, just using this. They were a little bit vague in the paper of the exact details of what they actually beat and stuff, but this is a really interesting and simple approach. So they trained this using binary classification here because they wanted to compare to the in-production models. And then they also, basically we might want to get a score like area under the curve, AUC, etc. So then we can check what is the probability of tokens. So will they apply? We might say yes or no, and we can check, all right, what is the probability of the next token being yes? What is the probability of the next token being no? And we can use that to get scores. Another approach that people are going is that they're saying, okay, we were still autoregressive RecSys. Instead of going in text domain, we go into item tokens. So we say, okay, we have interaction history of our user, which is they might have watched Stranger Things, then they might have added one to watch later, played another series, liked that one, and then they watched 4 episodes or 3 episodes of Stranger Things. And then we can basically see that as our tokenized history, right? The items themselves are the tokens. And the thing here is like the other approach for 360 Brew with LinkedIn might work very well because their job postings are kind of more in text domain directly, right? The movies are harder to bring into text domain. They're naturally a separate token. So this was from Netflix this year, where they basically explained how they built this recommender system. We see similar approaches from Meta. So Meta released a paper called Actions Speak Louder Than Words, a huge 1.5 trillion parameter recommender system that is really good because I watch Instagram Reels and I can see, how hooked I get. And basically, their idea is, all right, well, the posts are the tokens. And then we have basically they separate them. So basically, they have content tokens, which might be the Facebook post, might be the Instagram Reel, etc. And then they have an action token, which is, well, did the user, like this one? Did they comment? Did they? How long did they watch the reel? And then we train this auto-regressively. So we do next token prediction, similar as we do for LLMs. So I really want to emphasize this. They're seeing, basically, we can do it directly in text domain, which is like we just use a pre-trained LLM. But other, companies see it as, all right, well, the key innovation here is the next token prediction paradigm. So that we can take that and just apply it, but we change what we see as tokens, and but we train it in the same way. So what are the challenges in autoregressive RecSys? So one is obviously latency, where if we do it in this text domain, it becomes quite expensive. These models are 100+ billions parameters. The one from Meta, 1.5 trillion, and so it takes a lot of engineering effort to make them work. In text domain, I think that increases the inference cost quite a bit, instead of doing it like the other approaches we saw in item tokens. But the pro is that we get better cold start, because the LLMs are already trained, right? We don't need a lot of data to start using them. And for item-based, the memory requirements, they can explode very quickly. If we imagine, for Meta, they have billions of users, they have billions of posts, right? And all of them needs to get stored, right? So it takes a lot of embeddings to store them. And I imagine, from that total 1.5 trillion parameters, I would not be surprised if over 1 trillion of those are just stored, cached embeddings, and only a few 100 billion might be active. The third challenge is that RecSys is non-stationary. We require constant fine-tuning. We can't freeze them like we do for LLMs. We train LLMs, we freeze them, then we interact with them several months later, and they still work fine. But for recommender systems where we introduce new items, users constantly interacting, we need really sometimes very complex engineering flows to do training in a streaming way where we record the actions of the user very quickly and then fine-tune. All right, key takeaways. 1, LLMs are great for cold start. RecSys agents are really powerful, and if we just hook up tools, we can use that directly. LLMs are great human simulators and can be used for evaluation. And thirdly, autoregressive RecSys is taking over. We see it in text domain, item domain, or we can imagine hybrid solutions like we saw. We can do a mix of text tokens and item tokens. So this is a very interesting thing to follow. And you can do other things with autoregressive RecSys as well, like beam search, etc., with the same kind of methodology. All right, that's it for me. Thank you for listening. These are my points.
Okay, thank you so much. So we do actually have plenty of time for questions. So here we go.
Great talk. It was very interesting. I have a question about the simulation of humans, because I think it could be a problem in the sense that we have seen the psychophancy with GPT, so that the model tend to agree with you, you know. So I feel that maybe some models, especially the commercial one, maybe the closed ones, might be biased to give better scores or to imitate, or I don't know, to help or in some way bias the results opposed to a normal user, I would say. Do you think it could be a problem or not?
Yeah, so I think if we look at those papers, they basically take validation set as well. So the scores might be inflated, if that's what you're saying, right? The scores might not be in the same category or the same distribution as a normal user. But basically, we can change that by how we evaluate as well. So those papers usually, they take out interactions that for validation or test data for what they actually rated those movies. And then they can see, how closely can we rate the movies that they actually rated with our simulated users that are based on their personalities. So that way we can check, all right, well, how close do we get? And if it would be that, this has an inflated distribution, then we could easily just shift to get it closer.
Okay, questions? Another one. Super.
Hi, thank you for the talk. You mentioned the autoregressive recommender systems, but they seems like just the pre-training phase. Could you tell more about how they, I don't know, fine-tune them to, I don't know, increase the interaction or this kind of stuff? So like the reinforcement learning from human feedback equivalent in the field.
Yeah, so that's very interesting. The approaches currently are mostly based on supervised fine-tuning. So they don't use reinforcement learning or anything like this. But I would say RecSys usually is a bit behind, right? So they look at what other papers and what they're doing in the field, and they try to see how can we use this in recommender systems, like graph neural networks, self-supervised learning, and so on. So I would say that we can, sorry, what was your question again? I lost track of my thought process.
What is the equivalent of the last fine-tuning?
Yeah, so we haven't really come to that point, was what I'm about to say. I wouldn't really say that there are any reinforcement. There are some that are exploring that, but none that are really the main method used by the big tech companies right now. But what would be really interesting if you ask me is, all right, well, if we take that generative agents approach, for example, right, could that somehow be an evaluation that we could use to then improve incrementally our recommender system, right? So if we have a really powerful evaluation, we can use that in some way and integrate with how we train using reinforcement learning.
Okay, more questions? Anyone? Let's see. Okay, I do have a question for you, Aladdin. So you were talking about Reels on Instagram, and sometimes I see a lot of similar stuff, but maybe every 4 or 5 or 6, I see something that is so different. So I was kind of wondering, if you can tell us, maybe why that is happening, maybe for engagement, how will that, can be working in practice under the hood?
So I don't think anybody actually knows how they work under the hood. But we know how they were trained, right? So they were, that model I showed you, by the way, for Meta, that is in production now. So the LinkedIn paper, they haven't put that into production, but the Meta one is actually in production, and it did improve the performance quite a bit. But yeah, I mean, they look at millions and millions of, maybe perhaps billions of users, right? And they learn really complex interactions of this and instill them into parameters. And they do so in a very, engineering impressive way, where they, when you watch a reel, right, they basically store that and put that into streaming. Like they stream that 1 minute later. How long did you watch? 30 minutes later, update the model, and then that's the new one, right? So.
Okay, super. Thanks. So if we don't have any more questions, we can go to the next speaker. Okay.